Hello, you're welcome. All right, so now we are going to be talking about current electricity. Okay, so we've already looked at static electricity, and here we'll be talking about the current electricity. Now, what's current electricity? Current electricity is the type of electricity that is generated by continuous flow of electric charge. Okay, unlike static electricity or electrostatic where the electric charges are stationary, but in current electricity there's a continuous flow of electric charge across a conductor. Okay, so now this particular circuit diagram I use it to illustrate how static electricity work. Let's say this is a conductor. Okay, let's say a cylindrical metallic conductor. Now for this conductor to actually, for current to flow through this conductor, then energy must be supplied to it in form of potential difference. So that is why you see me, okay, supplying energy from, and this energy comes from a cell, okay, or battery. Here it is a cell. So this cell possesses energy in form of chemical energy. Now this chemical energy is converted to electrical energy, which provides potential difference. And once potential difference is actually provided across, okay, a conductor, what happens? Current flows through it. So there's going to be current flowing through this conductor. Okay, here we current. So current will flow. And what is the flow of current? All right. Now current is simply the flow of charge per unit time, the quantity of charge flowing through a conductor per unit time. Okay, so we simply mean that this conductor, all right, has electron. Every substance has electron, and the electron is our charge carriers. So anytime you hear that current is actually flowing, it simply means that is a flow of electron, because it's electron that actually carries charge from one part of a conductor to another. So as you see me here, this is this entire conductor at every in the entire volume of the conductor has a flow. Electron is actually flowing through it, right? And the quantity of this electron flowing through this conductor per unit time is what we regard as electric current. So that is that. So what you see me actually showing you is the movement of electron from one part of the conductor to another, right? So now that actually brings us to the definition of electric current. Okay, now we use the symbol I, okay, to represent electric current. So now what's electric current? Electric current, okay, is defined as the quantity of electric charge passing through a conductor, okay, per unit time. The quantity of charge. So the Q there is the quantity of charge passing through a conductor per unit time. So this is the formula for electric current, and of course the SI unit of electric current is ampere. The SI unit of electric current is ampere, okay, abbreviated as A. All right, so which simply means that this conductor is being supplied with potential difference, and there is the flow of charge, okay, the flow of charge, some quantity of charge flow, okay, through this conductor. Now this is one formula for electric current. There's another way of expressing electric current. All right, now let's look at another form of expressing electric current. First of all, let's look at this cylindrical conductor, okay, and now let's actually consider the fact that the quantity of charge that is actually flowing through this conductor depends on the number of electrons. Why? Because, okay, electrons are charge carriers. In fact, one electron, E, okay, carries a charge of 1.6 times 10 raised to the power of minus 19. This is just a charge of the charge for just one electron. So now this conductor might carry thousands of electrons depending on the number of atoms. Okay, so now you can actually we can conclude that the quantity of charge, okay, of charge that a conductor, as in a conductor is passing through a conductor, depends on the number of electrons, okay, of the conductor. Let me use N to represent the number of electrons. Then multiply by the charge of one electronic charge. Charge for one electron, that is E. Okay. Now, since this conductor is not a plane, it's not a plane shape. It's a solid shape. That means it has volume. That means the entire volume of this conductor, that are electrons. Okay. So I still have to multiply by what volume? So this is another word for expressing quantity of charge. So quantity of charge is given as NeV. Number of electron multiplied by electronic charge for one electron, then multiplied by volume of the conductor. Now let's still continue, right? So now this is another way of actually expressing the quantity of charge. Now I'm going to be looking at how to, okay, I want to derive the formula of current, electric current, both based on the drift velocity. Okay, now two things are very important for you to note. The current flowing through this conductor first depend on the quantity of electron. Okay, the higher the quantity of electron passing through this conductor, the more current you get. Okay, and that thing that also the current depends is the velocity of the electron, the drift velocity. So the faster the electron move, okay, the rate at which electron actually passes this conductor per unit time, okay, the more current you get. So that is why I want to derive the formula of current based on drift velocity. How will I do that? Okay, let's do that. First of all, it's worth noting that anytime you want to, the volume of a conductor, okay, you want to evaluate volume of any particular shape. The volume of any shape is given as the surface area times height, okay, the base area times height. So in this case, I'm going to have base area, okay, of this conductor, then times the height now becomes the entire length of the conductor. Let's say the length of this conductor from here to here. So invariably the volume of that conductor, capital letter V, is given as base area times the length of the conductor. Okay, so that's number one. Let me call this relationship 2 or formula 2. Okay, let's now proceed. Now you also know that velocity, we know that velocity in physics is always given as a displacement, okay, and displacement here in this conductor, displacement of the electron is the length, okay, displacement divided by time, okay, we know that already. Okay, so invariably if I should cross multiply, remember this all over 1, okay, from this relationship I will simply have that the length of the conductor is going to be equal to the velocity of the electron, drift velocity of the electron multiplied by time. Okay, let me divide here so that I will continue. Okay, so from here now, substituting into this, that means the volume of my conductor is given as the area of the conductor, okay, multiplied by the length, and the length is given as the drift velocity of the electron then times time. Good. So now let me call this equation 3 now. Okay, substituting this into the original expression for quantity of charge. Remember I told you that quantity of charge is given as number of electron multiplied by electronic charge times volume. So here I have gotten the expression for volume, so I can go to this place now. I can simply say that, okay, the quantity of charge is giving us the number of electron times electronic charge times volume, and of course volume I have here is area, then multiply by velocity of the electron, then times time. So I've got to my quantity of charge. Now I can now get my current based on the drift velocity of the electron. So now don't forget that my electric current is given as a quantity of charge all over time, which of course is going to be equal to NeAVT, okay, then divided by the time. All right, so time cancels time, so that simply means that another way of expressing electric current is going to be N, the number of electric charges, times the charge for one electron multiplied by the area of the conductor times volume. Okay, so you can call this equation for or whatever, just atomize the equations. Okay, so it's either I will express my current, okay, as a quantity of charge all over time, or I express current based on the number of electrons passing through a conductor times the electronic charge times the area of the conductor, then of course times the velocity, the drift velocity of the electron in the conductor. So please take note of that. All right, so this is just what we're doing here. Okay, this is the introduction to um, electricity. Now let's actually proceed. Okay, now you ask yourself, if you have a conductor, okay, does electron just flow through that conductor without supplying anything or any energy to it? No. Okay, before electron can flow through a conductor, before you can generate current, there must be an energy, and that energy is in form of what is known as electromotive force. So we're going to talk about electromotive force. Now, how do I define electromotive force? And of course, I will define the electromotive force, then I now differentiate it from a potential difference. Okay. Now, electromotive force is simply the energy. Okay, that energy might be a form of mechanical energy, electrical energy, chemical energy, or whatever energy, okay, from a source, because definitely there must be a source of this energy, okay, from a source which is converted to electrical energy. Okay, that is actually used to drive, okay, electrical energy. So the energy, whatever energy it is converted to electrical energy, which provide potential difference, okay, which actually provide potential difference, that is used to drive current or to drive charge, to drive electric charges from one part of a conductor, from one part of a conductor to another. Okay, so that simply means that EMF we are talking about, the EMF, okay, that energy might come from, it might come from a battery. Okay, a battery can provide EMF. It might come from an electric generator. Okay, electric generator like dynamo. When dynamo rotates, it can provide EMF. It might come from even nuclear. It's a solar cell. Okay, a solar cell can also provide energy. Okay, in form of light energy, which is being converted to electrical energy. All right, so please take note of that. Now, how does that differ from potential difference? Okay, what's the difference between that and potential difference, PD? Potential difference, which also we call voltage. Okay, now potential difference is simply the work done. We use V to represent the symbol for potential difference is V, so we also call it, it's commonly known as voltage. Okay, the potential difference is the work done in moving a charge from one part of a conductor. Okay, work done on a unit charge. Okay, work done in moving a unit charge from one part of a conductor to another. Okay, work per unit charge. Let me write that in full. Work per unit charge. Okay, so, and the SI unit is volt. Okay, work done. And in EMF also, the SI unit of EMF is also volts. That means two of them are actually, they are the same. Okay, the only difference is that EMF, as you know, in physics, we say that energy is the ability to do work. Are you okay? While work is the actual movement of the actual force that is applied to move an object to a particular distance. Okay, so just take look at electromotive force as the energy, okay, which is actually stored. Then potential difference is the actual work that is done by the energy, okay, provided by that particular source, You understand the difference now? Okay, so invariably potential difference now is the actual work that is done in moving a charge from one part of a conductor to another. So both EMF and of course potential difference, they are being measured in volts. So which simply means that a cell provides energy, and that energy actually creates a potential difference, all right, across a conductor that drives current, drives charge from one part of that conductor to another. So these terms are actually very important, so you need to actually ponder on them, understand these basic terms, because it's going to form the basis of the things we are going to be learning under current electricity. Okay, so see you in the next video. Thank you very much.